Hello world, we're live doing some more LeetCode practice. And for today, we have picked a problem for today's practice. We're doing this medium level problem. And our first goal is to try to understand it. It's called construct. So let me try. Okay, I hope I'm sharing it, and let's start the clock. I'm gonna try to understand it first. Okay, so okay, it's 1:05. Binary tree from Preorder and Inorder Traversal. So I'm gonna use my super powerful tools, which is a piece of paper, pen, and pencil. White paper and pencil are one of my favorites. To help me get the graphical understanding. So it's a problem of the first 100. So it's one of the classics, I guess. It's about binary search tree, right? Oh no, it's about binary tree general. So, okay, so it's called, okay, we need to construct a binary tree, which is a graph, which is a bunch of nodes where there is a parent, and the parent can have up to 2 children, left and right. And each of those children can have their own children. And yeah, so that's a binary tree. Now, preorder and inorder traversal, I need to look those up because I can kind of remember that from these examples. So preorder is preorder 3920, so it's like node, left, right, left, right. So that's preorder. Yes, so preorder, order is node. Yeah, it definitely looks like we're going node and then left and then right. It starts like here. So it's like node, then left, and then right. And in order looks like we start with left, node, right. Yeah, so node, left, right. In left, node, right. Left, node, right, and because left, what 9, 3 node, but before we get that node, we again get left, node, then right. Yeah, so that's what those are. In order is we start, yeah, start here, left, node, right. And so given two integer, sorry, I'm a little bit distracted with some texts. I'll get back to them. Given two, yeah, we need to construct the binary tree given two integer arrays, preorder and inorder, where preorder is the preorder traversal, is the inorder traversal of the same binary tree, of a binary tree, and the same construct and return the binary tree. Okay, so what else do we know? What else do we know? We know that there's up to 3,000 nodes. They're all unique. Okay, this is highlighted. Unique values. They all have the same values. Is guaranteed to be the preorder traversal and guaranteed to be the inorder traversal. Okay. Let's get like from top down. If we just have a bunch of numbers, the thing about binary tree, just a binary tree, there is no order in it. You can create any type of tree. I mean, you can put create any kind of structure. So essentially, you could even create just one linked list out of it. Okay, like have it all go to the left or to the right, whatever. And yeah, so it could be just one linked list. Then node, and then node. But yeah, like graphical representations. But the fact that the preorder has this type of order, that gives it that sets the structure. Okay. Because yeah, if we just had an array and the point was, okay, give us, I don't know, like any binary tree, so then we could just start by building, okay, whatever, let's go in some, we can like even do one long right branch, or we can do both branches, like left and right, and then do left, build them by rows, left and right. By the way, to build them by rows, we would need to do, well, we could do we would need to do breadth first search, yeah. because, yeah. But the preorder Inorder is all depth first search. And that's why this happens when we go like 9-3 and we don't hit the 20. We hit the 20 node, but we don't return it. We hit that node calls for 15, so we go to the depth of it. Now, how do we use these order guides? And I guess we need both. So why do we need both? I wonder why we need both. So if we just have preorder, well, preorder is like 3,920. So at least that starts with a node. 9 doesn't even, that's the root node. So if we have 3, so we know preorder starts with the root. Let's say we just have this preorder guide. So what could we do with it? Like let's say we have this 3, 9, 20, 20, 15, 15, and 7. So this is preorder. So we know we need, okay, we start with 3. Then the next one could be, it depends, because 9 could be left branch, or if there is no left child, then it could be just right child. 9 could be the right child. Information could be the preorder from the right child. Okay, let's put it that way. So yeah, it depends if there is a left child or not. So this doesn't tell us. So it could be like that, like the one in the picture, or it could be a bit different. It could be like 3 could go to the right. Then could it? Well, the simple case is 3 would go to the right, and there needs to be a 9. So if there is no, one of the cases is there is no left child, there are no left children, so it will always get you the child and its right, and the child and its right. So preorder is, wait a second, no left. So it's node left right, which is node left right. Yeah. So we'll get node left, node. So if there's no left, we will always just get the right. So yeah, so that's, by the way, one of the cases. Or it could be also, yeah, so it could just go no and then 9. Or it could be that 3 does have, yeah, so again, 3 goes to not to the right, but on the right, there is 9 is the node again. Yeah, 9 is the node. Could be 9 goes to 20. But it could be 9 goes to 20 is the left. And then 15 is the right. And then there is just 7 that could be anything. So it doesn't give us enough structure, yeah. So I guess we kind of understand, like in 15 minutes, we kind of understand part of the problem. And I guess that the just in order also is not enough. If we just use in order, it's also not enough. Doesn't give enough to build the binary tree. Yeah, because with this, we could build a lot of different binary trees. Okay, now we have also in order. So what does it tell us about a node? Because I guess preorder tells us it starts with a node. Okay. So this is just preorder, which is NLR. So just NLR gives us that. But if we have NLR plus left node right, then we have, okay, 3. We know 3 is a node. We know 3 is a node, so we have, yeah, so we have 3. So this is like 20, 15, 7. And this is 9, 3, 15, 27. So we have a 3. That's where we start. And I have a 3. We know it's a node because preorder starts with a node. It's a root, a root of a. By the way, does this mean that this is going to be the root of the entire tree? This first one. Node left, right. I guess so. It's gonna be the root of the entire tree. Where else would it be? Yeah, so it starts with the root, then it goes whatever the left branch returns, then it does whatever the right range returns. Yeah. Goes left. Then we go to the depth. Yeah. So left. Okay, that's good news. At least we think we know the root. So that's root. Yeah, I think I'm small little win. And then we go to the right. Well, we want to know for this specific node, okay? Let's try to simplify and just build that one subtree. Yeah, that one little subtree, that 3, that 9, and that 20. Can we? Yeah, we got the 3. Now to get, yeah, we need to know, is there anything on the left and on the right? So if there is something here, then we know that this next number is either a left or right, based on preorder. Yeah, but we don't know which one. Now that's why I will look at the Inorder, and we'll look at 3. We need to find it though. I mean, we can look at 9 and see, okay, what is 9 and what the Inorder is a left node right. This is like node left right. This is left node right. So it's essentially they are the opposite. But they start with, yeah, they start at different positions. Look, this starts at node and goes counterclockwise. This starts at root. I mean, the first one starts at root, and the second one starts at child left and goes clockwise. So this one is here. This one goes clockwise from left to right. So based on that, this 9 could mean it's the leftist, the most leftist left that you can get, because it's the entire tree starts on the left, starts with this thing. Yeah. If you go in order, you start with the left node. You print first the left node. If it node has a left node, then you don't print the root first, you also go to the left. So essentially, each node, for each node, it will start with the left. When we go to the depth of it, it will get you the left node. It's the left child, it's root, it's the node, and it's right. And then it will go up. So at the bottom, so that's what it does. You see, that's how it works with a node, with each node. It just takes its left, it prints it left, prints it, like here, 3, 9, 3, but instead of 20, because there is more, so 1527 is, when they're the last, that's what you're gonna get. That's what you got. We would get that on the left side as well, if there was something else. So that's the leftist one. We know that a child does have a parent. Yeah. Although with preorder, the parent might not have the left child. It might not even have a right child. It might be just a node. So if there's only 3, that's all you're gonna get, and that's the node. If there's something comes after that, this is how computers work. They don't see the entire thing. They see the one value at a time, like opening boxes. So so when we look at the second value, there is a second value. We see 9, but we don't know what it is. Now this one will tell us. And by the way, the preorder, which starts with no, then goes to left and goes to right, if there was something more than 9, it would print 9, right? Because if there was a full node here with children, it would give us node left, right. Node left, right. That's what it would print. X, it would print this X9, XYZ, ABC. Oh, wait, no. It would be like node left and then right. So it would go, it will start with the node and then go to its left child and then go and give its right child. So it prints node, then it prints left and prints right. It's a bit I'm trying to wrap my head around it because it's a bit counterintuitive. It's not how we human read from left to right or like clockwise. This is counterclockwise direction, and that weird thing is printed here. So I'm trying to understand what if there is a left node. Which is the question we want to know. Is there a left node? And what is it? Is there a right node? What is it? So if we have something, we know that one of them exists. If we look at the Inorder, and by the way, that's a good algorithm, a good approach, simple. Like we see a number. Could we go to the Inorder and learn, is it left or is it right node for our 3. Could we? Let's see, because Inorder always starts with the leftist thing you can get, right? Yeah, and it doesn't necessarily have a left child. 9 could have been also a root. Of the tree. So like then 3 would be its right node. Could be 9 and 3. But we already know that 9 has to be a child of 3. So it looks like if 9 is standing before 3, that could suggest that 9 is the left child of 3. Yeah. Because, yeah, eventually that's what we want to get. We want to see like, okay, here is a root node. Then 9, okay, what is it? Left or right? Left or right? And by the way, I'm thinking which of these orders give us a simple actually, okay, first of all, both of them are depth first search, so we're not gonna get breadth first search out of them. I'm thinking, I'm guessing. So if even when we combine them, as we go further, we are not going to get breadth first search. We're just gonna go depth. Okay, because so we'll read them and build our tree in the depth order first. Traversal. Depth first search traversal. Yeah, DFS. If that's the proper right way to say it. And by the way, we are 30 minutes into this. I think we're like halfway in figuring out the solution. Yeah, because computers, they're pretty simple. I mean, you want to just go over these numbers. And yeah, when you see 9, yeah, the 3 we got already what 3 is. We demystified 3. 3 we understand from the preorder. Now 9 we see and we're like, okay, we don't know from here, but we can assume looking at the Inorder, we see a 9. We know it's the leftist thing you can get. 9 is the leftist thing. But one thing, yeah, that's for sure. It might not be yeah, from the Inorder, we don't know. Inorder, it's just left node, because left node right, we don't know if 9, when we just look at the 9, we just know it's somewhere on the left, which could be like very deep down from that root. Could be. and I don't want to, but we know it's on the left. Is that already enough for us to tell that the 9 that we're looking for is a left child of 3? I think yes, because from here we know that the 9 is a child of 3. The preorder goes like, does it like 9? It goes node, left, right. No. Well, it could be that this 9 is actually a child of some descendant. Could it be? Could it? No. Preorder starts with the node. So whether it's left or right, it always starts with the node. So 9 is the parent. The parent. Why do we call it node? Maybe we should call it parent. I don't know what they use, like in order. I think, yeah, if you like preorder, traversal, if we Google it, preorder, traversal, node left, right? I think that's how they, yeah, no, they call it node left. Yeah, node. That's the, yeah, node left, right, and that's left, node right. So 9, when we see a 9 in preorder, this one, we know for sure that 9 is itself starting this problem. Oh, look at that. I just noticed there's actually this, this indicator that shows how many people are starting this now. Yay, wonderful. Live, like all around the world, 100 people are starting it. Gee, I wonder if how many people are starting the other one. 24. Okay, that's the other one. This is similar, but it's from Inorder and Preorder construct. Yeah. Okay. Wow. Yeah, this one is 100. Gotcha. That's good. Now you feel a little bit more, like united with social. Yeah, you feel a little bit more social. LeetCode is 63 now. Okay, it changes pretty quickly. Water. I'm talking a lot, which is my practice to kind of work to get a better understanding, to practice getting my thought process across. Yeah, articulating my thought process. So 9 is a child. There it is in itself. Yeah, the in order could give you some descendant, because yeah, it starts with a node. It could be a node of the node of the node. So left, yeah, but preorder is definitely gives you a child. Definitely gives you a child. So since we have 9 here, yeah, I think it's pretty obvious that 9 is something on the left. Yeah. By the way, in order, I mean 9 could be, if there's nothing on the left, and then the in order would start with a 9. Could be a parent. But in this case, we know the tree doesn't start with the 9. The root is not the 9. So that means 9 is something on the left. That means it's a left child. Okay, now I kind of understand it. Let's see if we can get something else. Okay, from here, we figured out the 9. And we know that in order, then goes to the right. In order, then goes to the right. And here we don't know. I mean, it could go to the right or it could get its children. So 9 might have children or might not, we don't know. Yeah. From preorder, we don't know, because this 20 that comes, it could be the left or right child of 9, or we could be done with 9. It could be the right child of 3. But if we look at in order, we continue looking at it in order, we'll see that 9 has 3 as its parent. Which tells us that, well, as a human, I understand that this is left, and that always go to the node. Every child has a parent in a tree, in a binary tree. There is no children without a parent. So that means if we directly, after 9, if we directly got the 3, that means 9 is a leaf. Yeah. So, and my first, I think we should have a sort of a recap, preliminary, or some. I should have some. What do you call them? Interim result check. Interim result, yeah. Or interim, is that the word? Intermediate, interim. Yeah, in terms of time, so this is like interim. Interim result check. It looks kind of, I mean, for a human, it looks a little bit overwhelming, because I'm trying to, like, I need to switch over those orders, traversal orders and use deduction to like deduction to exclude options and get the, because and by the way, it's probably a good exercise to oops, wants to see copy. What is that? I don't understand. See text and image comment typically. Wow, this is the first time LeetCode is asking to see the copy. Okay. I'm okay with that. So in order, so we're trying, I mean, it might be a good exercise to try to do that without looking at this. Yeah, that's how computer will do that. Yeah, so it will exactly how. Yeah, just like that is probably is an exercise, is the way to go here. Yeah, I'm thinking that's probably the way to go, because I need that. I need that logic. So we know this is a node. Yeah, it might be just easier to say, okay, that this thing is, we need to traverse it like that. Node left, right. This thing we need to traverse like that. Left node, right. And these are our and from here to try to build it. And we left off where we saw that it's 9. We know 9 is on the left, and on the left, and then we see here that left node, right, the 3 has to be a node for 9, right? A parent, 3 is the parent for 9. What else do we know? And by the way, then 15, we don't know what 15 is. This one left node, right, this node left, right. So node left, we figured out, but then that 20 that comes after it, we don't know where it is. Left node, right. And by the way, I knew that this problem would be a bit tricky. I don't know, for some reason for me, this going from the linear numbers to the tree structures, from linear structures to tree structures is a bit unusual. Yeah, so now without looking at the picture, I'm trying to where comes 20? We know, I don't even remember, because I don't remember where 20 is. So node left. So this is like node left, right. But 20 could be here, or 20 could be one of the children of 9. But the left node right, that tells us since 3 is the child and 9 goes 9, since 3 goes after 9, since 9 is the leftist one, and then comes 3, so 3 is not a 3 is the parent. 3 comes right after 9. For Inorder, that is parent. So always a parent. Next number is always a parent for the left one. Right? If it's the left. Yeah, for the left one. Left node right. So from this, as a human, I can see that, okay, 9, so yeah, their structure, so we know 9 doesn't have kids, 9 is a live, 3 is a child, so that means that 20 is a right child of 3, right? Yeah. Gee whiz. But how do I know that? I know that from all these deductions, but I mean, it's too many. It looks like tons of ifs. Because 9 is the first in this entire array. So we know that 9 is the leftist. Then we have a 3. Because 9 begins the array, we know is the leftist, but because 9 is not the beginning of the preorder, we know it's not the root. So it's always like deduction over deduction. So if 3, yeah. So there are some deduction rules here. I'm curious. So now we're close to the hour, and I'm curious, how long is this solution? I think I've proven myself enough that this is quite so I just want to see, I want to remember the solution. I want to see, okay, this looks like about a page. Gee, how about that? How about that? That's like five lines of magic. 5 lines of magic. So I would say for me personally, these manipulations, the different traversals are already confusing enough for me, I would say. That's my interim result check. But when you try to go reverse, that's the next level of complexity. Because the logic that I was using here it was like, for human, it's kind of, we deduct, but to write all those ifs, like, it doesn't seem, it looks like it's gonna grow to get too confusing. So I think the way to go from here is to study the solutions that are already implemented, especially these ones. This one just use one function that's being recursively called, and I think that's probably the way to go. They even use slices index. Slices index? What is slices index? The way to go is to study the solutions. This field is too confusing for me to solve these problems. I think I'm like a couple of layers, or at least a couple of layers of complexity, of confusion away from having a clear understanding. So I need to study. It will be faster for me to study through those, looking at the completed solutions. And that's where I'm coming to, as I'm going through these problems, I'm coming to understanding, to an idea that it's probably better to, many of these problems are probably better to study. That's what I'm doing now, not only practicing solving them in a time crunch situation, but also I'm learning first. So many of them I need to learn, like, what's going on here, why, and it's because otherwise it's like reinventing the wheel, a lot of wheels, because why are they using goal? Slices index. What is this? Returns the index of the first occurrence of V. So it's a search. Slice finds the first occurrence. That's kind of, in terms of time complexity, I'm thinking like that's, they would look into the slice after 3000. First occurrence of this number. So it could be like n square-ish, but it's fine. It's just 10 million. Could be n square-ish. There are only topics here. They also talk about hash table. Well, not surprisingly. Divide and conquer. Very general. Tree, binary tree. Yeah, I guess that's the hour. And yeah, the primary conclusion is I would say 30 minutes, maximum an hour. If I see I'm too far, just look at the solutions, study them, and then do better learn the pattern first. I need to learn that pattern first before study before before trying to practice actually solving them in a timed setting, clocked setting. Okay, that's the practice. And I think I'll continue working on this problem. Following that plan. Thank you for watching, and we'll see you in the next video.